Have you ever just stopped and noticed how much is constantly in motion around us? But really think about
It's
it.
everywhere, isn't it?
Yeah. Birds flying, fish swimming, even our own blood flowing. Cars, planets, stars, it's just constant movement. But here's the thing that always gets me. If our Earth is spinning, right, and orbiting the sun, giving us day and night seasons, why don't we feel it standing right here?
That's a fantastic question. And honestly, it goes right to the heart of why understanding motion is so fundamental. It's not just casual observation.
Right.
It's a core concept in physics and absolutely critical if you're preparing for exams. You know, your class 9, 10, 11, 12 boards, UPSC, SSC, state PSCs, they all require really precise definitions and knowing how to apply them.
Absolutely. So welcome, everyone, to The Deep Dive. Today, we're tackling motion head-on.
That's the plan.
We're going to unpack how we describe it properly, sort out confusing terms like distance and displacement, look at different types of motion, and even get into using graphs and equations to predict movement.
Exactly. Our mission today is to give you a really clear, structured understanding based on those foundational principles. The goal is to equip you with the knowledge you need to ace those questions on your exams.
Okay, let's dive in. Where do we even begin? What is motion, fundamentally, and how do we talk about where something is?
Well, let's start simple. Think about anything moving, a ball rolling, maybe a leaf falling. What's changing?
Its position, where it is.
Precisely. Its position or location is changing, and that change always happens over time. So that's the core definition. Motion is the change in an object's position with respect to time.
Okay, simple enough. Change of position over time.
But here's a crucial layer. Motion is always perceived relative to something else, an observer or a reference point.
Ah, like on a bus. The trees outside seem to fly backwards, but the person next to you is still.
Exactly. Perfect example. That's why we need a fixed reference point or origin to describe location accurately. We say things like, the school is 2 kilometers north of the railway station.
The railway station being the reference point there.
Right. It gives us a clear starting point. Now, motion itself can get complex things, can move in straight lines, circles, they can rotate, vibrate, or combine these.
Wow, okay.
But for today, and foundational for most exam problems, we'll really focus on the simplest kind, motion along a straight line. Even those tricky thought experiments, like asking if your classroom walls are moving.
Right, relative to the sun they are.
Exactly. They're designed to make you think about this relativity and the importance of your chosen reference frame.
That makes sense. So, okay, an object is moving. What are we actually measuring? Is it just like how far it went in total, or is there more to it? I know distance and displacement often cause confusion. Can we clear that up?
Yes, let's nail this down. It's a vital distinction, especially for marks in exams. Distance is the easy one, conceptually. It's simply the total length of the path an object actually travels.
This is the total path covered.
Yep. It only needs a number, a magnitude. We call that a scalar quantity. So if you walk 60 kilometers from your starting point, let's call it O, to point A.
Your distance is 60 kilometers.
Correct. Now, displacement is different. It's the shortest straight line distance between the initial starting point and the final position. And crucially, it includes direction.
Ah, so it's got magnitude and direction, a vector.
Exactly. So in that first case, walking from O straight to A, 60 kilometers away, the distance is 60 kilometers. The displacement is also 60 kilometers, but you'd add in the direction from O to A.
Okay, so magnitude can be the same sometimes.
Sometimes. But watch this. Imagine you walk from O to A, 60 kilometers, and then turn around and walk back towards O, stopping at point B, which is, say, 25 kilometers back from A.
Okay.
What's your total distance traveled now?
60 kilometers plus the 25 kilometers back.
85 kilometers.
Right, your total distance is 85 kilometers, but what's your displacement? You started at O, you ended at B. How far is B from O?
Well, if A is 60 from O and B is 25 back from A, then B must be 60 minus 25, 35 kilometers from O.
Precisely. Your displacement is only 35 kilometers from O in the direction of O to B. See how distance and displacement magnitude are different now?
Oh, okay, that's a big difference. And here's the absolute key takeaway for exams. What if you walk from O to A, 60 kilometers, and then walk all the way back to O?
Distance is 60 plus 60, 120 kilometers.
Right. And your displacement?
Well, I started at O and ended at O, so
Yeah.
the shortest distance between start and end is 0.
Exactly. Displacement is 0. You can travel a huge distance, but if you end up where you started, your displacement is 0. Think about a car's odometer.
Yeah, it just keeps adding kilometers.
It measures distance. But
Yeah.
your GPS showing your route might tell you how far you are from your starting point that's closer to displacement. It's a fundamental difference.
That's crystal clear now. Distance is the total journey. Displacement is the straight line from start to finish with direction. Got it.
So we know how far in two different ways. What about how something moves? Is it always the same kind of steady movement?
Good question. No, definitely not. And we classify this based on how distance is covered over time. This leads us to uniform motion and non-uniform motion.
Okay, uniform sounds like pretty much. Uniform motion is when an object covers equal distances in equal intervals of time. Imagine a perfectly steady train covering exactly 10 meters every single second.
Okay, 10 meters, then another 10 meters, then another 10 meters each second.
That's uniform motion. Very predictable. But most real-world motion isn't like that. That's non-uniform motion.
So unequal distances in equal times.
Correct. Think about driving in city traffic. You speed up, you slow down, you stop. Or someone jogging might sprint for a bit, then slow down. You're covering different distances in each second or minute.
That sounds much more common.
It is. Most motion we see daily is non-uniform. In exams, you might get a table, like Table 7.1 in some texts, showing time intervals and distances covered. Looking at that data lets you figure out if the motion is uniform or non-uniform.
Right, you check if the distance covered in each time chunk is the same or different.
Exactly.
Okay, so we have types of motion. Now, how do we actually put numbers on how fast something is moving? And what about when that speed changes? This must be where speed, velocity, and acceleration come in.
Precisely. These are the key quantities for measuring the rate of motion. Let's start with speed.
Okay.
Speed is simply the distance traveled divided by the time taken. How much ground you cover per unit of time.
Distance over time. Simple.
Yep. Its SI unit is meters per second, MSA. You might also see centimeters per second, centimeter, or very commonly for vehicles, kilometers per hour, kilometers. Importantly, speed is a scalar, just magnitude.
No direction needed for speed.
Correct. We often talk about average speed, which is just the total distance traveled divided by the total time taken. Formula V equals S sec. So if an object travels, say, 32 meters in 6 seconds.
Its average speed is 32 divided by 6, about 5.33 meters per second.
Perfect. Or, like, example 7.2, a car travels 400 kilometers in 8 hours. Average speed is 50 kilometers. You might need to convert that to ems for some problems.
Right. Unit conversion is always important. Okay, so that's speed. What about velocity?
Velocity brings direction back into the picture. Velocity is essentially speed in a specific direction.
Speed with direction, so it's a vector.
Yeah, exactly. Same SI unit, MSI, but it's a vector. This means velocity can change in 3 ways. The speed can change, the direction can change, or both can change.
Ah, okay. So turning a corner at constant speed still changes your velocity.
Precisely. Because the direction changed. Now, average velocity is calculated differently sometimes. If the velocity is changing non-uniformly, it's total displacement divided by total time.
Displacement, not distance.
Crucial difference.
Yeah.
But if the velocity is changing uniformly, we can find the average velocity simply by taking the average of the initial velocity and the final velocity, VAV u plus v2.
Okay, 2 ways to think about average velocity.
Yes. And remember that swimming pool example, like Usha, in example 7.3, swims 90 meters one way, then 90 meters back. Total 180 meters, say in 1 minute 60s.
Average speed is 180 meters, 60s equals 3 meters.
Right. But what's her total displacement for the round trip?
Back where she started. So displacement is 0.
Exactly. So her average velocity is 0 displacement divided by 60s, which is 0 meters.
Wow. Average speed 3 meters, average velocity 0 meters. That really highlights the difference.
It's a classic exam point. Be ready for it. Okay, finally, what if the velocity itself is changing?
That's acceleration, right?
You got it. Acceleration measures the rate of change of velocity per unit time. How quickly is the velocity changing?
Okay.
The formula is A v ut, where v is final velocity, u is initial velocity, t is time. The SI unit is meters per second squared, MSO.
Meters per second. Makes sense.
And acceleration is also a vector. It has direction. If acceleration is in the same direction as velocity, the object speeds up, positive acceleration. If it's in the opposite direction, the object slows down.
We call that deceleration or retardation.
Yes, negative acceleration, deceleration, retardation all mean slowing down. Now, acceleration can also be uniform or non-uniform.
Like motion itself.
Exactly. Uniform acceleration means the velocity changes by equal amounts in equal time intervals. A classic example is an object in free fall near Earth, ignoring air resistance.
Okay, its speed increases steadily.
Right. Non-uniform acceleration means the velocity changes at a varying rate. Like that car in traffic, again, its acceleration is probably all over the place.
Makes sense.
Think about example 7.4, Rahul on his bicycle. He starts from rest, U0, and reaches 6 meters, V6, in 30 seconds, T30. His acceleration is 6 meters, 0, equals 0.2 meters, skip 5. Positive acceleration.
Speeding up.
Then he applies brakes, and his velocity drops from 6 meters, now u6, to 4 meters, v4 in 5 seconds, t5. His acceleration is 4, 6, 5 equals 0.4 meters, 6 feet 5.
You got to give acceleration, slowing down.
Perfect. Calculating acceleration in these scenarios is a very common type of numerical problem you'll face.
That's a lot of definitions and calculations. Speed, velocity, acceleration. It seems like graphs could really help visualize all this.
They absolutely do. Graphs are incredibly powerful tools for understanding and analyzing motion, especially for exams. We mainly use two kinds, distance time graphs and velocity time graphs.
Okay, let's start with distance time graphs. Time on the x-axis, distance on the y-axis.
Correct. Now, if an object is moving with uniform speed, what will that graph look like? It's covering equal distances in equal times.
A straight line starting from the origin and going upwards.
Exactly, a straight line graph. And here's the key insight. The slope or gradient of that line tells you the object's speed. Steeper slope means faster speed.
Slope equals speed. Got it. What if the object is just sitting still?
Then its distance isn't changing over time. The graph would be a flat, horizontal line parallel to the time axis, 0 slope, 0 speed.
Makes sense. And non-uniform speed.
That won't be a straight line, it'll be a curve. If the curve gets steeper, the object is speeding up. If it gets less steep, it's slowing down. You can see this in graphs like figure 7.4, often based on data like table 7.2.
Okay, so straight line for uniform speed, curve for non-uniform, horizontal for rest.
Yeah.
And slope gives speed? Clear. What about velocity time graphs?
Similar setup. Time on the x-axis, but now velocity is on the u-axis. First case. Uniform velocity.
So constant speed and constant direction. Velocity isn't changing.
Right, so the graph will be
a flat horizontal line again. But this time, it represents a constant non-zero velocity.
perfect. A horizontal line parallel to the time axis, like figure 7.5. Now here's another crucial insight for velocity time graphs. The area under the graph represents the magnitude of the displacement.
The area under the line tells you how far it went.
Exactly. For uniform velocity, that area is just a rectangle. Its area is velocity multiplied by time, which we know equals displacement. S is V is T.
Wow, okay. Area equals displacement.
What about uniform acceleration?
If acceleration is uniform, the velocity is changing steadily. So the velocity time graph will be a straight line, but slanted, like figure 7.6.
Going upwards if accelerating, downwards if decelerating.
Precisely. And what do you think the slope of this line represents? The rate of change of velocity over time.
That's acceleration. So slope is acceleration on a VT graph.
You've got it. And again, the area under this slanted line still gives you the displacement. If it starts from rest, it's a triangle. If it starts with some initial velocity, the area looks like a trapezium. Like in figure 7.6, you can break it down into a rectangle and a triangle.
Exactly. You calculate that area and you have the distance traveled. For non-uniformly accelerated motion, the graph would be a curve of some kind, like in figure 7.7. The interpretation principles, slope, acceleration, area, displacement still hold, but the calculations become more complex, often requiring calculus later on. But understanding these basic graph shapes and what slope and area mean is fundamental.
So graphs give us a picture, and we can extract speed, acceleration, and displacement from them. That's really useful. But can we go further? Can we actually predict motion with equations, especially that nice, predictable, uniform acceleration?
Yes, absolutely. This is where the three famous equations of motion come in. These apply specifically when an object is moving along a straight line with uniform acceleration. They are workhorses for solving numerical problems.
Okay, the big three. What are they?
First is the velocity-time relation,
Right.
V equal u plus at. It connects final velocity, v initial velocity u, uniform acceleration a, and time t.
VU plus at. Got it. Finds final speed.
Second is the position-time relation, s equals plus f where 1. This links displacement s with initial velocity, time, and acceleration.
S, E1's plus 1 is S. It finds how far it went.
And third is the position-velocity relation, 2s equals v11 is cu. This one is useful when you don't know the time or don't need it. It connects displacement, acceleration, initial velocity, and final velocity.
2S relates speed and distance without time.
Okay, these three equations are your toolkit. They can actually be derived directly from those velocity-time graphs we just discussed.
So the graphs and equations are linked.
Deeply linked. Now, applying them is key. Look at example 7.5. A train starting from rest, UA0, accelerates uniformly to 40 km/h. Convert this to s in 10 minutes. Convert to seconds.
First equation, VU plus at, gives you the acceleration.
Right. Then maybe you want the distance traveled. You could use the second equation, s plus 1/2 dyno, or the third, 2s(e)y1. Both work.
Example 7.7 is about braking. A car brakes, producing a uniform acceleration of -6 millisat. Notice the negative sign for deceleration. It takes 2 seconds to stop.
We can use v equals plus to find the initial velocity u just before braking. Then we can use s plus halfward, or 2s equals vvo1u to find the stopping distance s.
And that stopping distance calculation has real safety implications, right? Like keeping distance between cars.
Absolutely. Physics in action. Mastering these equations, knowing which one to use based on the information given, and being meticulous with units, that's crucial for scoring well.
Definitely seems like practice with these equations is essential. Okay, we've covered straight lines pretty thoroughly. But things move in curves, too. What about circles? Can something move in a circle at a constant speed but still be accelerating? It feels wrong.
It does feel counterintuitive, doesn't it?
Yeah.
But the answer is a definite yes. It's called uniform circular motion.
Uniform speed, but moving in a circle.
Correct. And it is accelerated motion. The trick is remembering what acceleration means. It's the rate of change of velocity.
And velocity includes direction.
Exactly. Even if the speed, the magnitude, velocity is constant, if the object is moving in a circle, its direction of motion is constantly changing at every single point.
It's always turning.
Always turning. Since the velocity vector, which points tangentially to the circle, is continuously changing direction, there must be an acceleration. This acceleration is actually directed towards the center of the circle, but the key point is change in velocity, even just direction, means acceleration.
Okay, that clarifies the paradox. Constant speed doesn't mean constant velocity if the direction is changing.
Precisely. Think about smoothing out a polygon. An athlete on a square track changes direction 4 times. Hexagon, 6 times. Octagon, 8 times. As you add more sides approaching a circle, the direction changes become more frequent, essentially continuous.
That's a neat way to visualize it. Is there a formula for the speed in this case?
Yes. For uniform circular motion, the speed v is the distance of one circle, the circumference 2r, divided by the time taken for one circle, t, the period. So v, v, 2 par t.
Okay, v 2rt.
And you can see this direction change in action, like activity 7.11, swinging a stone on a thread. If you let go, which way does it fly?
It flies off straight, tangent to the circle at the point of release.
Right. Proving its velocity vector was pointing tangentially and changing constantly to stay in the circle. We see this everywhere. The moon orbiting Earth, artificial satellites, even a cyclist on a circular track at steady speed. They are all undergoing accelerated motion.
Fascinating. Constant speed in a circle is acceleration. Another key point for exams.
Definitely. So let's quickly summarize the absolute essentials from our deep dive today.
Great idea.
Okay, first, motion is fundamentally a change in position over time, always relative to a reference point.
We distinguish distance, total path, scalar, from displacement, shortest path start to finish, vector, includes direction. Displacement can be 0 even if distance isn't.
Right. Then we have uniform motion, equal distances and equal times, and non-uniform motion, unequal distances and equal times.
We measure the rate using speed, distance times scalar, and velocity. Displacement time or speed with direction, vector.
And the rate of change of velocity is acceleration. Vector can be uniform or non-uniform. Remember, positive means speeding up in direction of motion. Negative means slowing down.
Graphs are key visual tools. Distance time graphs. Slope gives speed. Velocity time graphs. Slope gives acceleration, and the area underneath gives displacement.
Absolutely. And for uniform acceleration in a straight line, those 3 equations of motion are your problem-solving toolkit. VU plus at, SU S plus half at ca. 2S is VUONE all way. Practice them.
Finally, uniform circular motion involves constant speed but changing direction, meaning it is accelerated motion. Speed is v equals 2rt.
Master these points, understand the definitions precisely, know how to apply the formulas and interpret graphs, and you'll be in excellent shape for the motion-related questions on your exams.
Fantastic. This has been an incredibly helpful deep dive, clarifying so many crucial aspects of motion. Hopefully this gives everyone listening that solid foundation needed for board exams, UPSC, SSC, and all the others.
That's the goal. Keep practicing the concepts and the numerical problems.
Absolutely. For more exam-ready insights and concept breakdowns like this, make sure you subscribe or follow The Deep Dive. We'll be back soon with another topic.
Stay tuned.
So just to recap, in this episode, we covered the following topics: defining motion and reference points, distance versus displacement, uniform and non-uniform motion, speed, velocity, and acceleration, graphical representation of motion,
Yeah.
equations of motion, and uniform circular motion.